Hi everyone, welcome to the last talk in this session. So this talk is by Dr. Jiang Shaofeng. So Shaofeng is assistant professor at Centers on Frontiers of Computing Studies, Peking University. He got his PhD degree from University of Hong Kong and worked as postdoc researcher at the Weizmann Institute of Science. And today, he will introduce his recent work about streaming algorithm.
It seems that there was some network problem in this venue. Can you hear me and see my slides? So shall we continue?
I can hear you, but I cannot see your slide.
I see. So that probably is the problem. Can you see it now? No?
No, there is no slides is sharing now.
Okay.
Okay, we started. Okay, I can see your slide.
Okay, great. So let's continue. All right. So yeah, so I assume the data points is from the two-dimensional discrete grid points, means that every data point is a two-dimensional vector, and it is of integer coordinates with the range from 0 to delta minus 1. So, and then I assume that the points are presented in a dynamic stream. And the data set X that we care about is the set that we end up with. This means, so let's look at an example. So the dynamic stream could look like the following. So you could insert a point, let's say 0, 1, and then you insert 2, 1, and then you delete 0, 1 again. So eventually what you end up with is this 2, 1 point, 1 point only. So that's the setting. And what we look at is algorithms that have sublinear space, and this is usually the what the streaming algorithm look at. So we want to use little o of x, where x is the data set, little o of x space to compute the statistics of x. For instance, it could be maybe diameter or minimum spanning tree and so on. And we ideally want it to be done in one pass only. Scanning of the stream in one pass. So note that here we want little o of x because big O of x space is trivial because you can store all the points in your memory. So that's the algorithm. And what we want here is, so at least for this talk, we want an estimation for the statistic that you want. And that is only a real number, which is the value of the solution. And we see the value E, the estimation E is alpha approximate if it's at least the optimal and at most alpha times the optimal. So here we consider a minimization problem. So still note that here for many problems, for instance, this MST here that we mentioned, storing a full solution already requires omega x space because it takes all these edges connections. So it makes the problem trivial. So we want to consider the estimation version of the problem where we only care about the value of it. So that's the setting. And we consider a problem called standard forest, but let's start with a special case called standard tree. So let me define standard tree. So in the standard tree, we are given a set of terminals. This data set X, which is, as we said, is two-dimensional integer grid. And the goal is to find a minimum weight metric graph that connects X. So let's look at an example. Okay, so there's a very related problem called minimum spanning tree. And in this example, I'll illustrate the difference. So let's consider this example where the red crosses is a data point. So I have 3 data points. And I arrange them in a equally distant way. So they form a regular triangle. And let's say each of the distance is 1. Okay, each of the distance is root 3. Okay, so the minimum spanning tree simply takes these 2 edges. But the minimum standard tree could be different. It could actually use an internal point here, which is not terminal. And as you can compute, this cost is actually 3, while the minimum spanning tree is 2 times root 3. So this right solution is actually lighter or shorter. And it means that this non-terminal point, which we call standard points, it really matters in obtaining the standard tree. So this standard point, the presence of this standard point is really the difference between standard tree and the minimum spanning tree. Standard tree and the minimum spanning tree. And okay, and we look at this standard ratio, which we define as alpha 2. So here 2 means two-dimensional space. In general, we can define alpha d for d-dimensional space. And this alpha 2 is exactly the ratio between MST and standard tree, and the worst case ratio. So basically it means that if you want to approximate the standard tree using MST, then this ratio in 2 dimensions is alpha 2. Okay, so, and this is called the standard ratio, or you can think of it as a gap between MST and standard tree. So currently it has been shown that this alpha 2 is at least 2 over root 3 and at most 1.21. And actually this 2 over root 3 is achieved exactly by this example. And it has been conjectured that this alpha 2 equals 2 over root 3 is actually tight. But this has been open for decades. So this is so-called Gilbert-Pollack conjecture. Okay, so this is a standard tree. So what about standard forest that we consider? So in addition to a set of terminals x, each terminal is assigned a color in some predefined integer k. So it could take color 1 to k. And now let's say these colors, each of the, so we can partition the data set into, like, according to the colors, and partition it into k equivalent classes. So we define C1 to Ck to be the color classes. And the goal is to find the mean weight mean metric graph that connects each of the CI. So let's look at an example. So here, the blue triangle is one color, and the red crosses is another color. Okay, so this actually is a solution, right? So each of the color is connected. But the thing is that this solution could be disconnected as a whole. And furthermore, it could be that the optimal solution, even if k is larger than 1, the optimal solution could use like just one component, like this. So really, the disconnectivity and this complication of like components is the key challenge of this problem. And in the streaming setting, the associated color is also presented along with the points. So in our setting, the standard forest problem, we know this k in advance, and along with the point stream, we also learn the color of each of the point. So that's the setting. And we want to find approximation algorithm for this geometric standard forest in streaming setting. So before we go into streaming setting, present our result in streaming, we like to reveal some results in offline setting, because this standard forest is actually very well studied in offline setting and for decades. So first of all, in general metric space, it is NP hard to approximate within certain value, which is currently best value is 96 over 95. And the current upper bound is actually 2 approximation by using a primordial approach. And this 2 is surprisingly hard to beat, and now it's still open question to design an approximation algorithm better than 2. So towards breaking this 2, there are several other approaches where like using other types of techniques other than primordial. For instance, there's a Kruskal style greedy algorithm, and also local search algorithm was also considered. But both of them didn't succeed to break this 2, and they only achieve some constant ratio that is bigger than 2. But they do suggest some promising approaches. So for special metric spaces, for instance, our Euclidean space, there exists a pitas. For the problem means that 1 plus epsilon approximate, but polynomial time. And similar pitas also hold in other more general spaces, such as W matrix, and in graph metrics, particularly bounded genus or tree-width graph and minor excluded graphs. All right. But going to streaming setting, this problem is still largely open, and our result is both a lower bound and an upper bound for the problem. So for the lower bound, we show that every streaming algorithm achieving any finite ratio requires omega k space. So recall that k is the number of colors. So finite ratio basically means that you cannot distinguish between zero and non-zero cost using little o of k space. Okay, so and we actually obtain a nearly matching upper bound in terms of space. So our upper bound is alpha 2 plus epsilon approximate algorithm with space and per update query time, poly k over epsilon times log delta. So in terms of the dependency in k, our space is nearly optimal. And here this alpha 2 is indeed the standard ratio in 2 dimensions, which we mentioned in several slides ago. So previously, even for the only known result is for the special case of standard tree where k equals 1. So we know that for standard tree, there is an easy algorithm that gives the alpha 2 plus epsilon ratio, and this is exactly by using the MST. Recall that this alpha 2 is the gap between MST and standard tree. So if I want to approximate the standard tree using MST, then I exactly suffer this alpha 2. And previously, there was a streaming algorithm that gives a 1 plus epsilon approximation for MST in one pass. So we can use this and simply use the solution times alpha 2 as the estimate. But for general standard forest problem, nothing has been known for streaming setting. All right, so that's our result. And let's talk about the technical challenges. So when you think about how to solve this standard forest, I usually would like to think of it as a 2-step minimization problem. So since you look for the optimal standard tree, which forms a partition of the data set, so in the first step, I'd like to enumerate the connectivity. So basically, I need to group the k-color classes into several parts. Could be 1 part, 2 part, and could be k parts. But there could be many possibilities, and k to the k at most, so which is huge. And when you fix this partition, you can then apply a standard tree algorithm on each of the group, and that would give you an optimal solution eventually. However, this standard tree is very difficult, particularly because of the presence of the standard point. And in this work, we basically ignore the difficulty or omit the difficulty of this standard tree, and we just use the MST to replace the standard tree. And we suffer an alpha 2 ratio for this second step. However, if we do this, then we only have a very small space or very small room for the error for the first step, because in total we want alpha 2 plus epsilon ratio. So then it means that we need exact algorithm, or at best 1 plus epsilon approximate algorithms for the connectivity step. And that's exactly the challenge that we tackle. So previously, there are several known approaches for solving geometric streaming algorithms. And I think this is the first work that suggests this geometric streaming setting. INDIC shows that you can use hierarchical tree embedding HST to obtain order log-in ratio for various problems. And the problem of this approach is that this ratio is too large, which we cannot accept. So later on, there are several results for another class of problems, and they are quite successful. So we can use CoreSat to obtain 1 plus epsilon approximate for key median and facility location problems, and they are sort of clustering related problems. And the problem of this CoreSat is that they usually need some locality of the problem. For instance, in this key median, what we really care is not the key point, the relationship between the endpoints together, but the relation between endpoints and some k centers. So the real complexity of the problem is actually k. And this kind of approach is unlikely to be helpful for tackling these global problems such as MST or our problem. And so more recently, there's a 1 plus epsilon ratio for MST, and this is the most related work for us. But still, what they do is just uniform sampling. But since we need this sophisticated connectivity, so this uniform sampling is unlikely to capture this. So we will need more complicated steps in order to adapt it. So our approach is somewhat non-standard in streaming setting because we use a dynamic program. So when you think about dynamic program, usually there's the biggest problem is that you have a large number of basic sub-problems. So for this standard forest, as I mentioned, in Euclidean space, in offline setting, there was a PTAS. And in that PTAS, they use the Aurora-style dynamic program, where you divide this whole space into chord trees. So divide it into recursively divided into this kind of squares. So you start with the biggest square that includes the whole data set, and then you evenly partition it into 4 sub-squares, and eventually you stop until you reach singleton squares, which consists of only 1 point. And this subdivision introduces omega x, where x is the data set, omega x number of basic subproblems, and the space cannot be better than that. However, so what we can do here is to use another idea is to use an alternative set of basic subproblems. So basically, we want to use a small set of simple squares to replace these very small singleton basic subproblems. And so these simple squares could be larger, could consist of many points, and eventually we want the number of simple squares to be small. And on the other hand, it has very beautiful structural property to allow us to compute the subproblem on it. So as a big picture, so essentially now we define a new set of subproblems. And then we show that this subset of problem is small. And then we design an algorithm that can well approximate these new basic subproblems. And eventually we will get this alpha 2 plus epsilon. So here we can show that one can find order k log delta simple squares that cover the whole data set using space k polylog delta. So what do I mean by simple square? By the way, a square R is simple if no color class Ci is a subset of R. What does that mean? It means that so for every simple square, it can only contain at most 1 color class. It cannot have 2 color classes, okay? So, and intuitively, this could be constructed in a top-down approach. So the idea is quite simple. You can basically, whenever you start from the root square, whenever the square is not simple, you subdivide it into 4 subsquares, and you recurse until you reach a square that is simple. And eventually you can show that during this procedure, because of this definition, you will have order 1 simple squares per color, per level. So that's why we have this k polylog delta. Okay, so this is the first part of our approach. And then the remaining part is how do you solve this this new basic subproblem in order to do DP? So, of course, we cannot use the original dynamic program to do that. So we need an alternative approximation algorithm for that. But still, the property of this, so observed by Aurora et al. And previous works about this structural property of this simple square is quite useful. So essentially, we only need to consider the solutions of the following type. So first of all, the solution, so let's say we consider a simple square. The solution in a simple square only needs to cross this simple square order 1 over epsilon times at 1 over epsilon times log delta predefined portals. So as in this picture, this x is a portal. So before we do anything, we define order 1 over epsilon times log delta number of potential portals for every chord tree square, and particularly this simple square. And then we will choose at most 1 over epsilon sort of active portals to use, and we show that 1 plus epsilon approximate solution only needs to use this number of portals. So secondly, we further partition each of these simple square into gamma times gamma cells. So this gamma is actually a constant still. It is 1 over epsilon. And crucially, this simple square, the definition of simple square guarantees that we only need to consider the case where terminals in each cell are internally connected. So what does that mean? It means that even though there are many terminals, we don't need to care about how they are connected inside of a cell. And essentially here, we only need to look at the cells instead of the terminals. And the number of cells is 1 over epsilon squared. So essentially, to solve this basic subproblem, we only need to enumerate the connectivity between the cell and the active portals. So of course, we first need to choose what active portals that we want to use, and then we can enumerate the connectivity, so basically which cell connects to which terminal. And this enumeration only takes log data to the poly 1 over epsilon possibilities. And this is quite a small number in streaming, and we can sort of then we can sort of compute the sum of the standard tree for every enumerated component. So here I actually still follow the two-step approach as I stated before. So I first enumerate the connectivity of the solution, and this only needs to be done for the cells because we have the second property. And the second step is to compute the sum of the standard tree for each component. However, as I said, this standard tree is quite difficult because of the standard point. So I replace each of the standard tree with the MST. So sorry, there's something. Okay, so replace it with MST, and we suffer this alpha 2 factor. And now the technical challenge is that since we enumerate this connectivity, and it could create several disconnected connected components, and we need to compute the MST of each of the subset. So previously, there was a work that gives a 1 plus epsilon approximation for this MST value, but it does not support the subset query. It only computes the MST for the whole data set. So our technical contribution here is to design a subset MST query algorithm, streaming algorithm. But since this is only, it needs to support this stronger subset query, so it requires, unfortunately, it requires an additive error. So essentially here, our algorithm can answer the query with multiplicative error 1 plus epsilon, which is good, but the epsilon error is something like this. So when you look at it, this additive error depends on the whole point stream instead of the query set. So it could be quite large. And indeed, when you want to apply this theorem, you cannot just apply this as with the data set, because that could be too large, this error. So instead, we want to apply this theorem on each of the color. So, and then when we want to answer a query, we sort of combine these sketches for colors together. So by the way, here, linear sketch, we require that our streaming algorithm is a linear sketch, and the advantage of this linear sketch is that it's mergeable. So if you have a linear sketch for dataset A and a linear sketch for dataset B, then you can combine the linear sketches to answer the query for dataset A union B. So that's the idea here. So since I don't have much time, let's skip this lower bound proof. So okay, so let me conclude the talk by future directions. So first of all, I'd like to mention two directly related problems. So first of all, we assume in our work we assume that the data point is presented in an arbitrary order, arbitrary way. But what if the color classes arrive in a consecutive way? Can it help us? Can it give us maybe better dependence or even independent of K? Another related setting is that so for this standard forest, we actually have another popular setting which is called the pair setting. So in this setting, the input is not colored, but each of the input is a pair of terminals. And the goal is to find a minimum weight graph that connects every pair of terminals. And this could be reduced to the color setting in offline setting easily. However, we are not aware of any easy reduction to this setting in the streaming setting. So it would be interesting to study this model as well. And finally, I'd like to open the major open question here. is whether there exists a 1 plus epsilon streaming approximate polylog space algorithm, streaming algorithm for standard tree. Basically, our k equals 1 case. Thanks for the attention. That's all for my talk.
Okay, so thanks for the talk. So we actually have a question from the audience. It says like, can this this theory, these methods be extended to other metric?
Other metric?
Yeah.
Okay, so this I think, so first of all, I mean, okay, so this technique I think is heavily using the Euclidean property. So I don't expect it to be extendable to a metric that is much different than this geometric metric, but in this work we basically consider two-dimensional Euclidean space. But I do think it's possible to extend to maybe higher dimensional Euclidean. Yeah, but maybe it's not extendable to maybe graph metric and so on, which is quite different from Euclidean space. That's my take.
Thanks.
Right.
Can I ask a question?
Sure,
yeah.
please.
Yes, thanks for your nice talk.
Thank you.
I think the dynamic programming idea is quite not well used in the streaming algorithm. So do you think it have some other value in the streaming algorithm analysis?
Okay, I think
general model.
Sure. Yeah. Okay. So first of all, this particular way of use dynamic program in our setting is basically to adapt the Aurora's dynamic program, right? So I suppose this similar idea of maybe defining alternatives, basic subproblems, could also be applied in other type of dynamic programs. Yeah. For instance, it could be maybe edit distance and so on. Yeah. So, but I didn't check. This is a very interesting idea.
Yeah. I have another question.
Sure.
When I have some discussion with someone who is interested in the streaming algorithm, he told me a problem and explained it in a computational complexity view. So it basically means the streaming, the memory also can be viewed as a communication, something like this. Yeah.
Right.
So do you think it is a right or valuable view of the streaming model?
Okay, so I'm not sure what exactly he meant, but actually, so there's a standard way to prove streaming lower bounds using communication complexity. Yeah, and this proof is actually using such kind of reductions. Yeah, so essentially you can think of it like this. So first of all, what is one-way communication is that you have Alice and Bob, and they want to compute something, and Alice has some message X, Bob has message Y, and in one-way communication, it's only allowed to send a message for Alice to send one message to Bob, and they want to conclude. So, and why is this related to streaming? Is because let's say you have a streaming algorithm, and this streaming algorithm is used to sort of help you to do this compute this one-way communication problem. So you can first Alice use this streaming algorithm and input feed it with her input X, and then she can send the internal state of this streaming algorithm as the message to Bob, and then Bob continue the execution of this algorithm and feed it with the certain transformation of his message Y, and then conclude the value. So essentially, streaming algorithm could be used to solve this one-way communication problem, and that's why we can do the reduction to that. Yes. Yeah. So in this sense, it could be related to communication complexity, right?
Okay. Okay. So I think here ends this session, and thanks for all the speakers, and thanks all the audience.
Thank you.